I think we're live. Double check.
Uh, Yep, we're live.
All right. Hello, everyone, and welcome to Corecast. I am your host, Tim.
I'm Mikey.
And I'm Sahil. Welcome everybody to a brand new exciting episode of Quirkcast. Before we get started, if you haven't already, do join our Discord channel. And if you're watching on YouTube, we do this every Tuesday, 5 p.m. Pacific, 8 p.m. Eastern. Do ask us questions during the episode and we'll get to it. Also, we're in the process of putting out, making some shorts. So if there's any sub 1 minute explanations of any concepts that you would like, do let us know and we'll take it into consideration. So let's jump straight into it. So Tim and Mikey, this is an interesting episode. I don't think we've ever really talked about beauty and cataclysms in like one subject. And I think this will definitely give our audience like a interesting kind of journey of through the universe's history and whatnot. So I want to start off by maybe discussing what people may think that happened in the early part of the universe up till now. So you originally had the Big Bang, and then there's this really famous picture where it shows like everything at like a point-like thing, and then expanding out smoothly into like some early part of the universe, and then it just keeps going through time, and then it expands out again, and fairly smooth and like nothing too abrupt or anything like that. And even the conception of Big Bang, for those who are interested, is not an explosion. We've covered that in past episodes, so do check that out. But I want to talk about like after the Big Bang, when you see this sort of smoothed out kind of version. So could you describe maybe if that's right or if that's wrong and why that's wrong?
Well, maybe I'll just preface it, and then maybe Tim can go into a little bit more details. But I think like you hit the nail on the head. Like everyone's heard of the Big Bang, right? So, and usually people incorrectly think of this as some kind of explosion. But what it really is the creation and expansion, creation and rapid expansion of space at the beginning of time, and um, that's a pretty well-known story. And I think the purpose of this episode is to sort of fill in the details there, because you might imagine, okay, Big Bang happens, space is created, a bunch of particles get spread out, maybe they form into stars, stars ignite, form solar systems. But there's actually like a deeper story in terms of how the universe got to be in the particular state that it's in today. You might liken it to like if you're baking a cake, like a complicated cake that has many, many steps. Um, like I don't know anything about baking, but you could kind of liken the process of the universe's evolution to sort of like a complicated recipe that was baked into a very pleasant, inhabitable universe that we find ourselves in now.
Yeah.
Yeah, I mean, Tim, do you want to take that on?
Yeah, and I think this episode is also to dispel the notion that once the universe was created, it's kind of just a steady process of creating structures and galaxies and stars and planets. That's actually not the right picture. It turns out that the universe was actually a very, very violent place. There are many eras of very distinct behaviors of the universe, and then in between the transitions of these different epochs, there were violent, transitions. There are violent cataclysms that totally alter the way the universes are. Like if you go, imagine if you have a time machine and you're able to go back to the beginning, near the beginning of the Big Bang, the universe would be unrecognizable. Like it's not even close to what you would imagine. And also that hopefully by the end of this episode, our listener will realize that and this is still happening today. We are in an era of certain state of the universe, and eventually that will also change. The universe, like there's a propensity for our entire universe or just nature in general to go through periods of incredible changes, and sometimes these changes are not continuous at all. Just like it's like water boiling, or like I guess water freezing is probably a better analog. Like the universe can change dramatically, and that's what we're going to go through today.
I remember when I was in high school. I don't know if this is true because everything I learned in high school biology turned out to be wrong, apparently. But you remember that like they were talking about the theory of evolution, and I remember they called it the theory of punctuated equilibrium. And it was the idea that evolution doesn't happen steadily and slowly over time, but it like goes through long periods of nothing, and then it just jumps all of a sudden.
Mhm.
Yeah, but independent of whether or not that has any validity in biology, it does kind of share some kind of like metaphorical similarity with what we're talking about in the universe.
Yeah, I think that's a great groundwork for this episode. So let's jump into this. One thing I wanted to ask you is maybe it might be helpful to, we're not describing necessarily the Big Bang, but the starting point of like what the universe is like. Tim, you mentioned the word violent. Maybe it might be helpful to describe what that means. What does violent mean? Is it like particles bumping into each other, or yeah, what is yeah?
Yeah, I would categorize violent as it in some sense it's probably the best use. It's the best example of the word violent because the before and after it's completely different. These are like these are real cataclysms, right? And we can use our previous episode as an example. So for example, today we notice that most of the matter we see is just matter. There's no antimatter, right? At some point in the universe, that was not true. Antimatter and matter coexisted. So what happened? What came to be? There's probably a period of annihilation between matter and antimatter. And as such, it creates a tremendous amount of energy. Like the before and after, it's unrecognizable, the universe. Before, there's a ton of antimatter. After, most of those antimatter annihilated. And in that phase transition process, there's a lots and lots and lots of energy involved. And this is, I think, a general lore of many of the phase transition that we see in our universe. Like if you go back to the beginning of the universe, we believe, at least in many of our theories, the universe started with more or less nothing. I would say, just like all the matter and energy is stored maybe in some field. If you buy the theory of inflation,
it's not nothing. It's just one thing. Everything is stored in one thing.
Right. Yeah. So the energy, the universe is more or less totally different from what we have today. And if you take that as the starting point,
completely featureless, meaning no part of it is distinguishable from any other part of it. That's how the universe starts. Completely featureless, just a completely blank canvas, but very high in energy density.
Wait, I mean, can we even like conceptualize that, like what it means for it to be indistinguishable everywhere, or is that like how does one even think about that?
Like if you take like literally, if you take any one box in the universe, like an empty box, and you measure the statistical properties inside, and every other box, you get exactly the same answer within some standard deviation. In the beginning of the universe, like right now, we have lots of different types of particle species, right? We have like electrons, protons. Or in the beginning of the universe, there was just one type of particle, if you even want to call it that, and everything was just stored in that one field.
Yeah, basically, if you take that as the starting point, there was a long way for the universe to become where we are today. We all started from.
Do you think it's fair to say that in the beginning of the universe, there was like a war between the matter and the antimatter, and that the matter won by a slight amount, and that this counts as a sense of violence?
Well, if you anthropomorphize it, yeah, you can sort of argue that. But we're not even there. we're not even there yet, right? So in the beginning there was
Well, you brought
energy.
it up.
Yeah. So in the beginning there's energy stored in somewhere. Maybe the inflaton field, if you believe in some of the theories of inflation.
Some grand
Maybe
unified field.
yeah,
Some grand unified field.
some sort of stuff probably has all that energy stored up. And
Wait, you're
probably
not making it sound grandiose enough. This should sound really grandiose, right? This is like the grand unified field. Very
sure.
grandiose.
Although the reason it's not grandiose because we don't have experimental verification of what it is yet. So because we don't know. But probably
Yeah, but there's some very
yeah.
tantalizing hints.
Yeah. So but let's just say it is that's what it is. So this is the origin of all things, you know. And then matter gets created. Particle and antiparticles get produced, basically. Maybe in equal amounts or slightly off from equal, depending on the theoretical model. But more or less is equal amounts. You know, there might be a tiny imbalance, but you know, yeah.
How does that happen, Tim?
Yeah. So, you beat me to it, Mikey.
Yeah,
we have to talk about the friction.
Yeah,
I would say a friction process.
That's probably the first phase transition, but it's speculative. Yeah. You know, and this is, if you believe in the inflation model, then there's this field. Yes, there's some friction encounter, and it goes back and forth for a very, very long time, like a pendulum swinging back and forth. But slowly, that pendulum, I think it's like, it slows down to some extent, right? And then as it slows down, it started to decay.
Wait, hold on a sec. Wait.
Yes,
I want to stop right there. Let's take a step back because we introduced a lot of different concepts. So all I got was there's one particle. I mean the essentially where everything came from, and then we jumped to matter, antimatter, and then now we're talking about pendulums. So can we link this all together? Like what? How is it going from one particle to matter, antimatter? Or what was the next step before?
Okay. Yeah. So as Tim mentioned, this is speculative, but like literally the simplest physics model you can write down looks like this. In the very beginning of the universe, there's all the energy is stored in just one field. So like there's just one particle species. People like to call that the inflaton. And that's sitting, that puts the universe at a very high energy density, and that's very crucial. But as the universe evolves, a process can happen that's kind of similar to water boiling or water freezing, where the energy can suddenly drop. There's like some profile in the energy of the universe. If you assume that there's just some non-flat profile, like the potential energy has some kind of curvature, then eventually this thing will slide. The energy density of the universe will get lower, and it'll sort of roll around at some minimum. And that rolling around, you can kind of liken it to like a friction. It just shoots out particles and antiparticles, that process. So just this very, very simple model of just a curving potential at the beginning of the universe gives you the creation of matter and antimatter from nothing.
So I want to conceptualize this a little bit more, give a bit of a more visual kind of picture. So could you imagine it like there's this landscape of hills and valleys, or hills and troughs, I forget what the exact terminology is. And you have this like ball that represents our, universe that's at the top of this hill. And this energy drop that you're talking about is as if the ball is rolling down the hill and then settles on this like local minimum, which is not necessarily the global. It could go lower, but maybe there's another like hill that's like, slightly high up, maybe not as tall as the previous hill, that's kind of blocking it from like going down even more. And so you're talking about like, if you imagine a marble rolling down that like one of those hills, that's this going back and forth. So can you tell me like that back and forth, how does that relate to producing matter and antimatter? Like what is this? Why does it need to even go down? Like what is like,
so I just want to
is energy going down, energy density?
When we talk about the hill, we're not talking about a physical space. We're talking in terms of like theory space. right?
Mhm.
So as like the temperature changes, right? Um, I guess the simplest example that people are familiar with is water, right? Like you have a theory of how water moves as a fluid, but then as you change the temperature, the description of how that water moves starts to change as it starts to change to ice, and you have to move from a theory of fluid to a theory of ice, right? Um,
Mhm.
and so this kind of you can kind of imagine this as going from one part of a theory space, like fluid, to like the
Mhm.
solid part of theory space. And that's what we're talking about. It like as the conditions of the universe change, your theory description can
Mhm.
change, the energy can change. And if we assume that the energy has some lower place to go as the universe evolves, then it'll end up there. And
Yeah.
these bounces essentially amount to fluctuations in the energy density of the universe, which just pop out particles. That's what it would look like.
Yeah.
Okay.
I, I also want to add one thing that, even though we may be talking, it seems like we're talking about one specific scenario. This is actually generic in some of these phase transition, although the details might vary a little bit. So what you have is, I mean, a very good analogy is like it's like boiling water, although the universe is
Actually,
cooling down.
is it the same? Could you describe it? I don't know. Naively, it seems like you a similar potential.
There are some differences, but the analog you can carry over, right? Like what happens with boiling water? Basically, you can think of the fuel as the density of the water molecules. Like gas, the density is much lower, and liquid is much heavier.
Mhm.
Because when the water is boiling, water can't decide: does it want to be liquid or does it want to be gas, right? And this is it's in the same way. Does the infotron want to be in one particular space of theory or the other particular space of theory, right? So there's this competing factor. There's multiple types, type 1 or type 2. And in the case of boiling water, it can't decide. So there are bubbles that form, and maybe when you're heating up a pot of water, it's more preferable for the water to be in gas, right? So the bubble will expand because the force of the bubble will eventually overtake the liquid now. And in the same way as the universe cools, one type of one configuration will override the other. So slowly you have these bubbles that are kind of forming that prefers one particular configuration over another. And in the interface between these bubbles, between one phase or another, you get changes, and energy is stored in these changes. And in these boundaries, things can get created. Matter particles can get created. Stuff can happen. It's not an exact analogy, but like it's like when in a pot of boiling water, you see the whirling happening. Like stuff is happening, and this
No, it's like
energy.
it's the bubble have its surface tension, and when it pops, the energy is released. So it's kind of like splash, right?
Sort of, yeah. But I don't know if it pops in that way. But yeah, anyway.
It's not. Yeah, it's not. Yeah, but kind of.
And and then I want to clarify, like you mentioned that like temperature, energy density of the universe is going down. I guess what's responsible for that? Like why did it even bother to come down? Why didn't it just stay the same?
That's an
Like you're
assumption.
done.
If
That's
you
it.
assume that there's only one possible energy density for the universe, then yeah,
Mm.
you can't have what we have right now. But if you assume that there is some place for the universe to evolve to lower energy, then you just automatically get everything the
Mhm.
same.
Yeah. Yeah,
I see. Okay.
ultimately, it's a tug of war between gravity and matter and energy. So the
Mhm.
universe, when more and more the matter gets created, there's a feedback mechanism to gravity because they gravitate, and that causes the expansion of the universe, or that causes it to slow down in some ways. It modifies the expansion rate of the universe. So on the one hand, the universe is getting bigger, and because it's getting bigger, things are bound to get dilute. So temperature is going to get driven down, right? But then, and this is why this is kind of like the knob of dialing the heat on the boiling water. Although you're dialing it down as opposed to heating it up.
Mhm. Got it. Got it. Okay. So what I have so far is early universe. There's this one thing, maybe the inflaton, maybe something else, but just call it inflaton for right now. It effectively the energy density or temperature of the universe went down. It like went down this figurative hill in the space of theories and reached some sort of local minimum where it's kind of wobbling, and then that produced like matter, antimatter. But I think like where does I guess maybe even a more like basic question is where does gravity come in? Did it come in before that, or is it like it went down one hill and then you got all the 19 species of particles? Like let's walk through like what
Yeah,
happened.
Oh yeah,
There's
no,
an
that was just
ordering.
the first. Should we start enumerating these like these
so
different
sorry. Yeah,
cataclysms?
let me correct one
Yeah.
thing first. In the beginning, in the very beginning, there's gravity, and there's no temperature yet. Temperature is only defined when you have stuff. If you have no stuff,
Okay.
there's no temperature. Or you can argue the temperature is zero, right? So the whole you can argue that the whole Big Bang begins when stuff gets created, and that's the first step. So matter particle is created, and then the universe start to heat up. This is the period of reheat. What's the word like?
We call it reheating. That's the
Reheating,
first
yeah.
cataclysm.
Yeah. So it reheats. So finally we can go through the Big Bang now, and the universe reaches a maximum temperature, and now it starts to cool down basically. So you get all kinds of particles, as long as they because there's a lot of heat going on, particles can create freely. There's so much energy available. If you want to make a Higgs boson, you make a Higgs boson,
It's like a
right?
plasma, yeah.
Yeah. If you want to make an electron, it's just going to make an electron because there's so much abundant energy. All particles of all types are getting created left and right without discrimination. Everything
Wait.
is
Let's
created.
back up here because Sahil asked specifically the question like, did all 19 appear at the same time? Probably not. But just to back up on what Tim was saying, like so we're talking about like how there was this process where matter just suddenly just came into existence because of this friction. You can imagine like rubbing, just like rubbing wood on wood and just creating heat, and that's just going to create all these particles. That's usually when people talk about the Big Bang, they mean starting there. And then, so when this matter antimatter gets created, is it a quarks electron? Probably not. Probably not. It's probably some higher species of particle that we have yet to be discovered, right? Come on, Tim, let's go through the. We don't know how many of these cataclysms there were, but probably it started out pretty simple, right?
Yeah, but let me add that quarks and electrons probably exist back then, but they're different because when the temperature is high, like many times we iterate, the universe used to be very symmetrical. Probably electrons and quarks behave in exactly the same way. They are they are almost indistinguishable. So sure, we call them quarks and electrons, but then they're nothing like the quarks and electron we see today. Although it's a lineage, right? So if you follow them back up, you see that that's the ancestor for our electrons.
Or they might even have been part of the same object back then.
Right. So probably we have some objects that we don't know that are grand unified objects of I don't know electrons and quarks and forces, or if you believe in supersymmetry, they're supersymmetric partners. They all are created without any prejudice. They are all equal basically, and we have this soup of just an overwhelming amounts of different types of stuff going on. But at the same time, they're also all the same. They're not indistinguishable from each other.
I think it's fair to say that, like, so if you ask about the question about like how do we get to 19 particles, we said we started from one. It was probably a gradual process where you go from 1 to 3 to 6 and then to 19. Or, maybe you jump to like 100 and go back to 19.
Wait, so hold on a sec. Tim, you were mentioning like indistinguishability, but like couldn't the particles created have different charges, for instance, and you could distinguish, or like what does that mean? Like in the early universe when there was a lot of energy, abundance of energy, there's still conservation of charge, right? Or is that not like applicable?
No, they can melt. Charges can melt together. and become.
Yeah. So charge will still exist, but probably if you believe in grand unified theory, you can have electrons with negative charges and positron with positive charges, but then these charges are unified with other types of charges. Maybe there's I don't know, a star charge or like a color charge. Maybe they're all combined into one. And because there's so much abundant energy, let's say you grab a particle, it has negative charge. The next moment, it can just be taken away because it's constantly coming in and out, and it can change the type of particles that is at. It can change charges, can change color, because you're in a soup of superheated plasma. So sure, charges are still conserved, but like it's not very meaningful to distinguish them at that point.
Got it. So I want to tailor this comment. Oh, go ahead, Mikey. What were you going to say?
Oh yeah, just super quick. I think the point that I want to make about this whole thing is that the question of how many types of particles exist, like right now we can say 19. I think that's the number. But if you ask that question, like at each epoch of the universe, the answer to that question is vastly different.
Yeah, I'm glad you now are. You mentioned the word epoch. I want to tie this back to the original motivation behind this episode, which is cataclysms. Can we talk about what cataclysms the universe went through and what that must have been like for increasing the number of species of particles till we get to what we see today, as from whatever is known.
I think it's pretty much a rule that anytime you change the number of particle species, everything blasts apart, right? Like, let's say suddenly, like, protons could decay or something like that, right? All of a sudden, every atom in the universe would just blast apart because there would be no charge balance to like pull them together. So that's what we mean by like a violent process. And this is exactly the kind of thing that has happened at least 3 times that we know of, but likely many more times than that.
Yeah. So basically, we're talking about like take the example of quarks and electrons. We know they're very different. Quarks are what made up of protons and neutrons and their antiparticles, and the electron is what orbits them. Their property couldn't be more different. They're very different types of particles. But in the early universe, we believe they're the same. But at some point, the universe has to cool down, and in a way has to create favoritism of one over another. It has to choose certain particles to have some property, right? Like for example, their masses have to be different, right? Electrons are light and quarks are heavier. When that happens, when that differentiation happens, it's a cataclysmic event. Basically, you're telling me that the universe has cooled down now, and all of a sudden there are certain fields or configuration that settle in a particular point in theory space, and it decided that, hey, electrons are going to be light, and it's not going to have color charge, but the quarks are going to have color charge. Now, all of a sudden, instead of being equal and all the same, they separate out, basically. And this has to come at the expense of lots of rearrangement of the particles, content, the way things are interacting. And probably a lot of energy, stuff happening basically. So the universe will go through dramatic shift when this era happened, and probably to put it in technical terms, this is when probably the ultimate grand unified symmetry is destroyed. When that happens, we probably go through another phase transition.
So I also want to clarify.
It's not unreasonable to think that, like, quarks and electrons, they look different to us now. But like, right, if you have like a really rich beef soup, as it cools down, the fat's going to separate from the liquid. I think that's kind of like how you can imagine that's how electrons and quarks came to be different, right? In the early universe, everything was all mixed up in the soup, and then it cooled down and they separated and they got these different properties.
I like that analogy. It's actually pretty apt. Okay, so like I guess with the different like so we've defined cataclysm as like when you increase or change the species of particles that are there that just rips apart the universe. So Mikey, you mentioned three that we know
It doesn't
of.
always rip
What
apart the
are these
universe.
three?
Oh yeah, the three. Okay. Wait, hold on. Given the wait, there's probably way more than three. I was just talking about this with Tim, and I think there's a lot of things that qualify that I didn't even realize qualify. But um, uh, I I was thinking of like I guess the first one we talked about, and then the QCD one, and then the Higgs one. But anyways, never mind those words. The interesting one is the one that made light first start shining, right?
Hmm.
Okay, can we talk about that? Right, because
Um,
light didn't always exist in this universe,
well,
right?
let's go through a few first, and we don't have to talk about them, but let's just mention a few key
Let's do only
ones.
the fun ones though. The funnest, most.
I'm not sure, but let's say, one. Let's start from chronologically. So there's reheating, and at some point
Yeah, reheating is the creation of stuff, just the
yeah.
creation
So
of like particles.
at some point there's matter antimatter that has the what we call baryogenesis. Somehow, we have to see, we have to create that seed that eventually lead to more protons than antiprotons. That happens somewhere, but not necessarily all the way in the beginning. But at some
So
point,
there's a war between matter and antimatter, and matter wins by a little bit.
yeah. But
So
there's
now
still a
there's a
lot.
lot of blood,
Yeah,
aka
yeah.
radiation.
Yeah, but keep in mind, there's still antimatter. The antimatter hasn't disappeared yet. It's still there. Then at some point, there's what we call the electroweak phase transition, which means that the weak forces and the electromagnetism, they used to be the same. They used to be buddies the same way. But then finally, the universe played favoritism, and they decided that the weak force is different from the electromagnetism, so they separated. So that was another phase
Yeah,
transition.
like another like the oil, like the fat and the water
Yeah,
separating.
the fat and the water separated. That was dramatic. And at some point,
And that was when God said, "Let there be light."
no, not yet. This is the electric phase transition, and then the next
Yeah,
one.
no, that's when. That's when.
Oh,
That's when the
okay.
photon became massless.
Because usually it's referred to recombination, but okay.
Yeah, no, that's when it became free. But this is when it became alive, right?
Sure. And then the one after is, so quarks at this point are still free to move around. There's no protons and neutrons yet. At some point, the quarks become unfree. They become bounded. So that's the QCD phase transition, the quantum chromodynamics phase transition. And
So those
then
are the two that we know for sure about experimentally.
Yeah.
And then I don't know what the third one is.
Yeah, and at some point atoms form because electrons were still free to move, and at some point, and that's what we call recombination. That's when light really start to fly freely across the universe. So that's probably the major ones, but there are also quite a few more phase transition in between. We can go into more details of those, but
But like, yeah, the story of the birth of light, that's a cool one, right? That took a couple different phase transitions to work.
So the birth of light could be said like this electroweak phase transition, which is there's this fundamental force, the weak force, responsible for nuclear decay at a high level, and then you have electromagnetism. Those originally were one force, and then when the universe cooled to a certain point, it became separated, and they took on different roles. And then there's also a phase in which things cool down enough where you got atoms. I mean, I'm ignoring the QCD one you mentioned about protons and neutrons forming, but that already happened. Then you got atoms, and because they're atoms, light can propagate freely. Is that right?
Yeah, you can basically imagine this as like in the very beginning, it's like this uniform soup, but as things goes on, it just clumps more and more and more and more, and then once atoms form, now it's clumped enough that there's like open space that light can pass through. But the creation of light itself happened earlier, but it just didn't have any space to travel. But then once things clump enough, now it can travel.
Is this before or after the Big Bang?
Oh, after it's about 380,000 years after the Big Bang.
Wait, I thought the Big Bang was the event in which like the first photon came out of that soup.
No, 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 no. The Big Bang we usually think of as this reheating thing, like when the ball is rolling at the bottom of the hill and stuff is just like matter and antimatter are just spewing out. That's usually when traditional Big Bang people refer to like the Big Bang.
Oh, I see, I see. So okay, so there's that very famous picture of like the earliest map of the universe when it was like a baby, the 380,000-year-old picture.
Yeah, yeah,
That
yeah.
was when that's basically the let there be light moment is what you're referring to.
Um, if you look at well, you're talking about those pictures where they show the universe going like this, and like
Yeah,
expanding.
where it's kind of this like oval. It's this
Yeah, yeah, yeah.
oval with like patches of like, hot spots, cold spots,
Oh
and
no, you're
all
talking
that
about
stuff.
the cosmic microwave background. That's the
That is the let there be light moment though. That
yeah,
that
yeah.
is.
That's when light finally can stream through the
Yeah.
universe. I
So
mean,
that's the earliest map of the universe made of light because that was the earliest time that light could fly.
So is that in relation to what you just described, those three different transitions
Yeah,
where electroweak, then protons and neutrons forming, and then atoms forming,
yeah.
was that picture after atoms had formed, is
It's
my
that's
question.
at the moment the atoms form.
Oh, okay, okay, okay. I
Yeah.
I guess so. You're saying it's because atoms formed that like there was enough space. Otherwise, everything was like just sort of like pressed up against each other, and light couldn't really do anything, even though it existed.
Yeah, because like remember light responds to charge, right? So when you have electrons and quarks
Mhm.
just flying around, there's charge everywhere. But once they pair up, now everything looks kind of neutral from far away. So now light can just fly around unimpeded.
Okay, okay, okay.
So
Gotcha,
it's
gotcha. So,
the
mhm.
neutrality, like yeah, things paired up and became neutral, and that was very crucial for the propagation of life.
Mhm. Yeah, actually, there's a few audience questions that have come in. One which I'll read towards the end of the episode, but one which I want to read right now, which is what is theory space? You
Hmm.
guys have mentioned a few times.
yeah. So
How would you
so
describe that?
I think we're trying to avoid a technical term, but I guess it's hard to describe this. So what we're referring to is
Oh,
basically this picture of this ball rolling downhill. Like, what is this hill that is rolling down on? And really, it's the amount of stuff in this quantum field, and the position of where this ball is. You can think of that as moving in the space of theories. Because for example, you take the Higgs field. The Higgs field has a particular value. If somehow we're able to artificially move it up or down a little, even just a little bit, that would dramatically change everything. Like the mass of protons could change, electron could change. So when we say theory space, we're really referring to these configurations of these quantum fields, such that when you nudge them a little bit, like crazy things would happen. And that's what happened in the early universe, where the value of these configurations can change.
I think
So
you can think
so
of it like
can
a much
we can
simpler
we?
example. What, sorry?
Oh yeah, Tim. I guess Mikey, you were going to answer my question. I would say, can we give like a simpler example,
Yeah.
even if it doesn't cover the full breadth? Like, can we
Yeah,
can we explain this to like a 10-year-old kind of a
yeah.
thing, like an explanation?
It's okay. This is going to be still a little bit abstract, but like
Mhm.
like let's say I'm in a spaceship that's going into the sun, um, but there's no windows, so I don't know that I'm going into the sun, and I'm performing a physics experiment, um, and I think I know how physics works because I'm like tossing balls up, and they're going parabolas, and I have a theory of Newtonian mechanics. But then my spaceship starts to enter the sun, and I start to realize that the laws of physics that I was using don't seem to be working too well anymore because everything's burning and melting and everything. Um, and so you can kind of imagine that as a like if I wasn't aware of what my spaceship was doing, I could imagine that I would actually have to adjust the theory that I'm using to predict my physics from the theory of Newtonian mechanics to a theory of like fluid dynamics. So that's kind of, you can imagine even that as like moving through this theory space, because literally your theory is changing. The equations you use to describe your environment are changing with time.
Gotcha. Okay, so and then we have another question is I don't know at what point in the conversation, but I guess how did it not create a supermassive black hole if all the matter was together at one point?
Well, it
Maybe
certainly.
this is talking about like, yeah.
I mean,
Oh, go
it's
ahead,
a
Tim, sorry.
it's a numbers game. It's a numbers game. If the energy density is high enough, it could have created what we call primordial black holes. These are black holes
Yeah, that,
before stars were
that
formed.
idea is totally in play.
That idea is totally valid. There has been experiment to search for these primordial black holes, because if they are just these little black holes floating around forming in the beginning of the universe, they will still be here, and sometimes they would walk in front of stars randomly, and we might see their light pattern change a little bit. But experiment has shown that we haven't found primordial black holes. So probably the density just wasn't high enough to trigger formation of black holes. But for supermassive black hole, it's probably a little harder still. It is plausible. It depends on your theory, but it's not a guarantee. You really need a very high density. Also, remember, the universe is still expanding still. So you have a counterbalancing force. It's expanding, so even though your density is getting larger, it's also getting more dilute at the same time. So it's a numbers game.
There could very well be primordial black holes out there, just maybe not enough for us to have like seen an obvious signal yet.
Right, but we can't see them because they're black.
Could I guess one question I have is, could we give the audience any sort of sense of like how small the universe was and compared to how it is now, like a scaling? Is it like 10 to the minus 42 times smaller, like, or
I think
yeah.
that's hard to think though. So like that's I think it's like, so people always think like the Big Bang means the universe was smaller before.
Mhm.
But the universe the universe is always infinitely big, right? It's kind of hard to imagine. Imagine I have like a grid, just like a square grid, right?
Mhm.
And then imagine that the size of each square goes to 0. There's still an infinite amount of space here. It's just that you have a grid it's a singularity. So obviously we don't know how to describe that, but it's a mistake to say that the universe was smaller before.
Yeah, I think you can say it mathematically, but in reality, the distances are not comparable, because if you take me, literally, if you trace all the particles that I was made of, let's say send it back in time with a machine, I would shrunk. Like, I would be so tiny, crushed into like nothing, right? So like the measure of distance is just not comparable. Like, you can't really take the distance in the past to compare in the front. But if you just mathematically look at the numbers, even though it doesn't make sense, yeah, the entire surface of the universe was probably way smaller than Pinhead, right? You can
The
stand in
observable
awe.
universe, but it depends on what do you mean by the observable? You mean the current Hubble sphere or the current
Yeah, the Hubble sphere,
scattering
horizon.
distance? It's very kind of
Yeah,
the universe. It's possible for the universe to get bigger, but have always been infinite. It's kind of a weird thing, but that's very possible.
So what you're saying is that like distances don't make sense as much because things were so squished together anyway that I guess maybe I'm having a little bit of a harder time understanding.
Well, I would say comparing I would say
Mhm.
comparing sizes and distances doesn't make that much sense. Of course, you can compare the raw numbers. You can say, well, if I take the size of my fingers, send it back in time, yeah, it's going to be super tiny. It's probably at the Planck scale at some point, right? But does it make sense to compare them in that way?
No, I mean, okay, no, like here's a comparative. Like, if you actually take like just a plain classical GR interpretation of inflation, then at the Big Bang, points that were infinitely far away were infinitely close together. So the scaling from now to then is infinite.
Yeah. It's also a little hard to track what is the boundary of the universe that you're tracking, because the horizon also changes depending on the rate of acceleration of the universe. The things leaving the horizon, things coming to the horizon. So
yeah, it depends on the matter density. That's not a fundamental property.
Yeah. So I mean, you can do this comparison on paper, and you see that it's depending on when you do the comparison, the universe was way smaller, but it doesn't. I would say the number you get isn't as shocking as it seems, if that makes sense, because these are not like real physical comparisons.
Gotcha. So I want to, come back to the very beginning of this conversation where basically the title of our episode is Why Beauty Needs Cataclysms. And we've done a whole long expose on cataclysms and the journey through the universe. But what does this have to do with beauty? Like, why do we even include beauty? So Mike, I'm going to first go to you on this one.
Yeah, so it's tough because we use the word beauty in a lot of different contexts, but I think in this case, what we mean by beauty is like the very particular and seemingly carefully arranged structure of the physical laws that allow for complex chemistry, like macroscopic structures like planets and stuff to form. All of these kind of like little idiosyncrasies about the laws of physics that allowed for these things to form. It required this kind of like, as we were talking about, sort of like wiping the slate clean. I'd almost like liken it to people might know that there have been 6 mass extinctions on Earth. And you might think that, oh, maybe you could think that like those 6 mass extinctions were necessary for us to evolve in the way that we did. And so I think, I don't know, it's kind of like an analogy there.
I want to challenge that a little bit. Is that I thought people generally in like physics view that like, the more just maybe more reductionist or lack of better words, like the simpler you go, like, they could probably say the most beautiful time in the universe was when there was just one thing, the so-called inflaton field, if that exists. And that would just be beautiful. You write down one equation, very simple, and everything came from that. So rather than this like maybe mess of like 19 different species of particles, why the number 19 is just this long, really long equation. So I want to give that rebuttal to your response.
No, totally,
What do you have to say?
So the reason why the one grand unified theory is beautiful is because the 19 things just magically come out of it, out of this one thing. That's what makes it beautiful. It's not just that it's simple; it's that it's simple, but it naturally gives rise to this nuanced complexity we see.
I would say given that perspective, in order for that picture, the grand unified picture, to even be in order for that to be considered, in order for that to be plausible, there needs to be a mechanism to create, more nuanced differences from that simple law. And that's why cataclysms are absolutely needed. Because otherwise you tell people, hey, guess what? All the particles in the world is one and the same. They'll say that you're crazy. Like, it doesn't make any sense. How can that possibly be true? It is true precisely because there are these cataclysmic events that drive a divide between the seemingly the same particles and eventually form the complicated world that we have.
Yeah, it's not unlike thinking back to how the Earth, 6 billion years ago was just like a mess of volcanoes and poison gas, and then a bunch of stuff had to happen, a bunch of rearrangements had to happen, and then, million iterations later, here we are.
Yeah. Okay, that makes sense. So we're nearing the end of our episode, and so I wanted to give you guys a chance, and then afterward I'll ask the audience question. It's slightly unrelated to this episode, but yeah, to give you guys in our tradition of any words of wisdom that beauty needing cataclysms has taught you.
Yeah, I guess I can go. I think, I think in my early years of learning physics, I always thought, oh, the equations are beautiful, the laws of physics are simple. Um, but but I think as you learn physics more and more, you realize that the messiness of the world is actually beautiful because it's the real world. And what's often not taught to us is that the laws of physics require these there are these cataclysms and these changes that allows us to even think about these beautiful laws. And sure, the equations are beautiful, but the implementation of it is messy. And that's what allows humans to even exist and even contemplate this. And I guess it gets a little bit meta. So even though I think physics, along with mathematics, it's a discipline where we appreciate like these theoretical beauty very much. But I guess what's more beautiful is that it is plausible. Like it works for this messy world. And I think it's kind of an underappreciated fact of some of these fundamental physics is that really at the end of the day what's important is that it describe our messy world, I think.
Yeah, we like the idea that messiness can arise from simplicity, right? Like I feel like that's kind of like a undertone for every creation story. And like religious notions of quote unquote purity, whatever that means. Um, but yeah. But I don't know. Independent of all that, I would just simply say that if you like where you are, you can't regret anything that got you here. 6 mass extinctions. I don't know how many dozens of phase transitions. I don't know how many uh, intermediate periods there were where structures formed and were ripped apart, but here we are. It's a good time to be alive.
I like that. I think one small correction, Mikey, is that regarding the Earth's history, not necessarily the universe. I think there's been 5 mass extinctions so
Really?
far. I mean,
Oh,
no, six is what people claim we're in right now. Like, I mean, again, that's
oh,
up for debate. They call
okay.
the Anthropocene as the sixth mass extinction, but that's a whole nother topic. I don't really want to get into that, but yeah, just small correction on that. But
Yeah.
I thought you ended it very nicely, so I give you credit for that. So I want to ask the audience this audience question, which is unrelated to this episode, but very much ties into what we'll most likely be talking about next episode, which is and maybe you guys might want to give a teaser of what do you think about this, but what do you think about the recipients of the Nobel Prize in Physics this year?
We were talking about this before. We both hate it.
I, I would say hate is a strong word. Surprise, I would say. Although it was just announced today, I think we will try to make an episode to make it somewhat more relevant.
We could argue that in some way you could argue this is like a biophysics type, like thermodynamic kind of thing. I don't know. Maybe there's really nothing else interesting happening.
Yeah, I'm excited to see how we relate this one back to physics. But anyway, so hopefully that answers your question. And, leaves the audience with more excitement for our next episode regarding this, most likely. So, on that note, I want to thank everybody for joining us. We'll see you all next week.
All right, thank you all. Bye.
Bye.
Bye.